When I look at this landscape, I see a number of different features. So, starting out from this upper surface here, I see that there's a zone of small bushes, and there's this light buff colored material between them. Similarly, I see really close in front of me all the bushes here, and this light colored sediment. And when I walk over there, I see that it's pretty fine grained. So, we're going to say that that might have been deposited by the wind. Fine stuff, maybe in the lee of these bushes, maybe there is some wind blowing over this way. Then, below this, I see that there's this tall, steep cliff, and I can see this large block that's fallen off the edge. So, we know there must be some sort of block failure process that's leading to the creation and detachment of these larger rocks. And we can also see that there's a lot of other small material because the bottom of this cliff is really just swimming in sediment down here and all around here. And it continues across to the other side of this canyon. Of course, down at the bottom of the canyon, there's going to be some sort of river. And we can see that because there's a steep gorge that is bounded on either side over here and over here. And also because this is a low, dryish environment, it's not a place where there's a glacier down below us. So I can tell you for a fact there's a river there. All right, what else do we see going on in the landscape? We see some evidence of humans, right? Creating these stairs, making it easier for me. And what I'm defining right now are actually different geomorphic process domains. But each of these process domains also corresponds to some different geomorphic transport law, whether it's wind that's moving material or flowing water or just instabilities due to gravity and positioning on the slope. There's some sort of process that's creating the landscape around us. And in order to understand that, we need to define what we call geomorphic transport laws, this large multi-syllable word, and we're going to relate these back to these geomorphic process domains. And that's actually kind of obvious, right? Because a glacier might have different rules associated with how it behaves compared to a hill slope or a sand dune. And then I'm going to introduce their link with mass conservation because this is actually the key as we go into the future for describing how landscapes evolve and change over time. So first off, all right, what is a geomorphic transport law? It's a mathematical relationship. So what that means is that it's not just sort of a fuzzy-wuzzy, oh, this thing happens and then stuff moves. It's actually a predictive mathematical relationship, so we can use this language of logic and quantification, called math, to be able to directly make predictions and see how close our predictions are to reality. And specifically, we're describing and predicting mass movement through the environment. And the last piece here is that when we combine these with a statement of conservation of mass, a geomorphic transport law can help us predict how a landscape evolves. So, how do they relate to process domains? Well, it's pretty easy. So over here in the upper left, we have this set of hill slope processes, and you can see that there are ridges here. Going back. So you can see the ridges here that I'm drawing, and that then there's material flowing down them and creating these actually little drainage-like things. And so there's actually going to be some amount of fluvial processes going on as well. But we have largely material just moving down slope. This is a picture of a river. This is Mount Elbert in Colorado in the background. This is Half Moon Creek, where I was helping my friend Nate Bradley out with his experiments to put gravel tracers in this river that are all tagged with RFID chips, just like you have in your university ID card. And using those actually locate where they went over time. So this is the fluvial system. And where hill slope meets fluvial, we're back in the canyonlands, where we can see this terrain, this high top plateau surface, and these pinnacles which are gradually eroding and sending new rock down into the river below them. So mass transport within each of the individual process domains can be described by one or a set of geomorphic transport laws. And sometimes these are similar, sometimes these are quite different, and they might be quite different even within the same process domain. So for example, sediment that's moved by water and sediment that's moved by wind might have some kind of similar physics that describe them, because the wind motion near the Earth's surface and the turbulent boundary layer is actually in many ways pretty comparable to the motion and turbulence of water near the bed of a stream. There are some important differences, especially that water is a lot more viscous and a lot more dense, but there's this fundamental kind of fluid flow creating tractions that then moves sediment. On a hill slope, though, you can have quite different processes associated with slow creep of material down a hill. You can think of just gradually over time, these soil particles are just, occasionally stumbling and bumbling down the hill. Or maybe they're being helped along by the feet of you and your classmates as you're wandering around a hillside. Is maybe there's something much more dramatic that happens, and there's a large landslide or a rock fall or a mass failure that in fact is this response to, I should say, that follows a different set of rules. So that might follow rules related to elastic failure of material and then transportation of that material downslope. So here's just a quick example that I have of a couple terms that we're going to use. So there's discharge, which is, I'm going to use volumetrically, so having length cubed per time, and discharge per unit width. And discharge per unit width is length squared per time, and so that's just looking at the discharge as it's happening through one piece of this cross section. And so I'm just saying right up and down through here. Let's just see what's happening. And so what you do is you take the width here, which I term B as the breadth, and just say Q, little q, is equal to big Q over breadth. So the reason I'm introducing these terms is because we're going to start to use them to think about creating a first really basic geomorphic transport law, perhaps the most basic possible. So on our way there, let's just give it some thought. So these discharges could include the discharge of things like water and sediment or hill slope material. We've talked about those. We can also talk about lavas. So in that picture I showed you, and I'm going to go back to it, there is a volcanic mountain range in the back, or rather a laccolithic, so intrusive rock mountain range in the background. And this mountain range was formed by magmatic and processes, and actually I'd have to double check if there were active lava flows at some point. I sort of think there were, but I'm not sure. La Salle Mountains, Utah. You can check it out. It can also include things like discharge of ice and regolith. So this could be hill slope material, so new powdery rock that's weathering away. Or, you can just have something like discharge of migrating cod, right? Because you can have the volume of cod who are passing through some zone per unit time. All right, let's just put together a simple, reasonable geomorphic transport laws. And I'm going to call this the linear stuff moves downhill law. And that's because what we have here on the left-hand side is this is discharge per unit width. And on the right-hand side, we have this term over here. And if you're not familiar with these curvy d's, it's a partial derivative. It just means that we're ignoring any other dimensions. And so we're just really kind of focusing, let's say, on a hill that looks like this and what's happening down this way. But we don't really care what's happening in this direction or in this direction. We're just going to focus on the one-dimensional problem. And this symbol right here just means proportional to. And so it's the same thing as saying Qx is equal to minus some constant times dz over dx. And dz dx, so that's going to be elevation over distance. And so this is actually just giving us a slope. It's giving us a gradient. And we have this minus sign here because we want there to be positive mass transport going downhill. If we didn't have this minus sign here, mass would move uphill, and that's not so realistic. And so that's what gives us this linear stuff moves downhill law. And I call it the linear law because there's a direct proportionality between discharge and slope. If this slope were raised to a power, for example, it would stop being linear because it would follow a curve. So let's move this, or combine this linear stuff moves downhill law with conservation of volume. So up here, this is steep. So this is a hill slope profile. So right now we have elevation. And then over here, we just have distance. And so you can see the steep zone here. There's a lot of material moving downhill. And this gently sloping zone here has very little material movement. And so if we have this sort of transport law, this toy geomorphic transport law, we're going to say that there's a lot more material that moves here than moves here. And that opens up a question, right? Because what is going to happen with all this excess material that moves in? Because of this, if you look at the size of this arrow, maybe it's able to chunk out that much of this and move it up, but we've got the rest of this arrow that's going in and not leaving. So where does it go? You've probably already guessed the answer. It goes into a new deposit. So that material doesn't actually make it out of the system, and it creates this zone here, which is new rubble. And that might look a little similar to what we saw in that first picture. And furthermore, that actually creates a steeper slope. So now we actually have a much smoother gradient between these two different slopes. And so actually we're seeing that it's possible that if hill slopes follow this sort of pattern, they might smooth themselves out over time. We'll get to hill slopes at some point, not too long in the future. Well, let's see about that. Does this actually happen? So this is me taking the Empire Builder past Mounds Park, not far from where I grew up. And what you can see is that there's a steep cliff here. Big cliff band, there's a railroad cut into the side of it, but and so that causes this overhanging limestone, the Platteville limestone, to appear and to look a little scary. There are actually springs and seeps right here. This is just more for your viewing pleasure. You can see nice icicles on these cliffs if you happen to pass them in winter, where there's water coming out of the base of the fractured Platteville limestone and above this layer of Glenwood shale. And then down here, this is the St. Peter sandstone. And what you can see is that there are these piles of debris, these streaks of debris that are then ending up in piles here and here and here and here, all at the base of the hill slope. So yeah, this sort of thing is happening in nature. And we can go back to our initial picture and we can see exactly this. So we have the steep zone, this talus apron, and that's this expression geomorphically of something that is probably not so different from our linear rule. Now, one question remains, right, which is why did this stay so tall and blocky? And why did this end up being this gentle apron? And why didn't it all just sort of diffuse away over time if we have this sort of linear rule? And we're going to be talking about that in the future, so stay tuned.